Hello.
Is everything okay?
Yes.
Okay. Nayara is not going to be here in the afternoon, but if you need anything, invite to our office.
Okay. Thank you. Sorry? Oh, you were blocked outside. Yeah, I was as well, but I got really lucky with the RNG, and like as soon as I showed up, someone else was.
Yeah, Bernard is not here today.
Jean Bernard is not here today. He told me he had some meeting at 2 p.m.
Okay, and I think he was going to be in Europe. In Europe.
Yeah, I think so. This is cute.
Yeah.
Okay, so before getting started with anything too technical today, I wanted to step back and talk about something a little bit more primitive, which is this idea in physics of time reversal symmetry. And so I can show you an example of a physical system that exhibits time reversal symmetry, which is this. Okay, so I can throw the object like this, and if you play the movie backwards, it looks exactly like this. But this is also going forwards in time. Okay. So naively, the way that we would do that is like the state of our system, which in this case would be perhaps the position of the ball. Let's say I have psi of t is the state of the system. Then naively, if you run the arrows backwards, you could say that psi of minus t is also a valid state of the system. Okay, now, if we only look at the position of this object, then perhaps this is correct. However, in practice, we know that in physics that an object has more degrees of freedom than just its position. We also have as independent degrees of freedom the momentum of the object. And if you look at both the position and momentum, this is not necessarily a valid solution to the defining equations of motion as well. To elaborate on that, so this state vector psi let's say I have some non-equal conjugate variables. I have Q is my position and P is my momentum. The way that I want to reverse this thing in time, at least for this simple system, is so I can take Q into minus. So I just simply reverse the argument of position in here, and for momentum, pick up this extra minus. If you additionally reverse the momentum of the object, you will generate the time reversal for the position. Okay. So perhaps if I wanted to be a bit more formal, I could say that this is represented by some map of theta, which acts on this. And so theta, in our case, will be this poly Z matrix. So in the case of maybe the dynamical system corresponding to a particle moving in one dimension, time reversal is implemented by this simple operation. So then there's a question of whether or not we could use this kind of logic to implement time reversal for more general dynamical systems. So this is for a classical particle. There's then a question of how do you implement time reversal symmetry in the context of quantum physics. And so if you try to do it like this, you might run into an issue. So we have, so in the context of quantum physics, the state of our system is governed by the so-called Schrodinger equation. So this is a linear dynamical system, and it's on a complex vector space because we have this imaginary unit I. And for the moment, I'm not going to put any assumptions on our Hamiltonian generator because I don't need to. So then if you were to try to say that, okay, let's suppose psi of t is a solution, implies that theta psi of negative t is also a solution to this equation. So to verify that, I can plug this into the left-hand side. So I would have I, and then because this function should not be time dependent, we can use the chain rule and just move the derivative inside. Let's see. So then this time derivative will pick up a minus sign from the argument of psi. But let me call this psi prime now so that I don't get too confused. So psi prime being the normal derivative of the original solution. And so then for this to work, we'll assume that this theta is invertible. And assuming that theta is invertible is not too big of a restriction. And the reason for why this is the case is that if you take time and you reverse it, then you should be able to reverse it again and get back to where you started. So in fact, assuming that theta is invertible is less restrictive than what you would probably want to do in general. So in general, you would probably want to even say that theta is involution. That so if I invert time reversal twice, get back to where I started. Okay, so but for now we'll just assume that it's invertible. And then I can move the minus sign over here. And so in essence, what I've learned is that this time reversal operator and this Hamiltonian generator need to be related in the following sense. So I need to have minus theta inverse H theta equals H. So that way, this state vector is then a solution of the original Schrodinger equation. Okay. Now, the potential issue that comes in mind is, let's say that we assume that theta is a linear map as it was over here. What that would mean is that our Hamiltonian is similar to negative itself. And so that naively presents an issue because for most Hamiltonians, their spectrum is not symmetric in this sense. This would imply that for every element of the spectrum here, that negative that element is also contained in the spectrum. Whereas for many physical examples of Hamiltonians, the spectrum will often be bounded below. This is a typical physical constraint that we assume that the spectrum of the Hamiltonian is bounded below, but not from above. And so for this constraint to be satisfied, that would violate this principle of having a Hamiltonian with bounded below, but not above spectrum. So then there's a question of how do you resolve this paradox, I guess, that in order for time reversal symmetry to hold, there has to be some unreasonable constraint placed on the Hamiltonian. So this was a problem that was solved by Wigner. So Wigner wrote on this in the 30s, also wrote on it in the 60s. So I guess he came back to it later. And one of the things that's maybe nice is, so Wigner, I think, originally wrote about this in German, and I'm not really able to speak in German, but you can find a translated copy of the works of Wigner. So you can find a translation of this original paper somewhere. So what Wigner said is, so, okay, we'll first move this theta over. So we still have minus h theta, this theta h. And what he did was he dropped the assumption that theta was linear. So he instead replaced it by the assumption that theta is not a linear map, that theta is an anti-linear map. And so I guess just as a reminder, what this means is, so if I give you two vectors, the superposition principle still holds. However, if I rescale a vector, so here's some vector space, alpha will be complex because I have that I over there. This has the effect of taking complex conjugates of these scalars. Okay, so an antilinear map is one satisfying these properties. And what he found is that if you go back here and instead assume that theta is antilinear, then you can implement time reversal symmetry without having to impose restrictive constraints on the spectrum of your Hamiltonian. Now, another thing that I'll emphasize if you have theta is antilinear, when we go through and take the inverse of theta on both sides of this guy, so I have to be kind of careful in this step here, because the first thing I have to do is move theta. I have to commute it with this factor of I, and that picks up a minus sign. So this minus sign becomes a plus. So first of all, by assuming that theta is antilinear, I've changed it from theta anti-commuting with h to theta commuting with h. And so now you might think, if you were to interpret theta as a linear operator, that this would place no constraints on what the spectrum of h has to look like. Because any operator can commute with some other invertible operator. You can always construct that. However, this constraint does in fact put constraints on the spectrum of the Hamiltonian, and we'll see that shortly. So the way to see that, we've been talking a lot about inner product spaces, and in the first lecture, I gave an argument that one of the physical applications of an inner product is that it generates conserved quantities for linear dynamical systems. So I might have to press a button. I pressed a button. So in a linear dynamical system, we talked about the existence of conserved quantities. And in this case, it would be some inner product that renders the Hamiltonian to be self-adjoint, or not self-adjoint, but symmetric. Something like this. So if you have this constraint, this implies that okay, this function is time independent, assuming that psi and phi evolve according to the Schrödinger equation. Okay, so Noether teaches us that conserved quantities and symmetries are in correspondence. And so this is maybe a guiding principle. Rather than thinking about this from an action principle, I'm just going to state this as a fact. There is a connection between conserved quantities and symmetries, and you could ask, what is the connection between the existence of a conserved quantity for your Hamiltonian like this and the corresponding symmetry? And the claim is that this conserved quantity, if it's non-degenerate, will exist if and only if there is an anti-linear symmetry. And then terms and conditions apply. You have to assume that your Hilbert space is finite dimensional. But yeah, so this is the first statement I want to prove. A theorem. There exists. Okay, let's say given H, which acts on a finite dimensional vector space. We say there exists a non-degenerate inner product such that H is self-adjoint. So this thing exists if and only if there exists an anti-linear symmetry. So by an anti-linear symmetry, we mean something where the inverse exists and that commutes with this operator H. So this is sort of a more precise statement of this correspondence between conserved quantities and symmetries. So let me see the path of least resistance to the proof. Okay, so the path of least resistance to the proof is to establish this first. So we talked about these guys, and we said that if this constraint holds, then this holds if and only if a certain constraint on the root subspaces holds. Namely, that the root subspace with eigenvalue lambda, it has the same dimension as the root subspace with eigenvalue lambda bar. So if I have this, then I have this constraint. So in essence, one of the ways to establish this theorem would be to figure out what the action of theta on the root subspaces would be. So suppose, so the lemma is going to be used to prove the upwards direction. I'm going to first assume that there is this antilinear symmetry. From that, figure out what the action of the antilinear symmetry on the root subspaces is, and then show that it satisfies what's required in order for this to exist. So let's see, we assume that theta satisfying these properties exists. Then we will show that theta acting on the root subspace with eigenvalue lambda is in fact equal to the root subspace with eigenvalue lambda bar. So if I can establish this, then this proves the upwards direction because theta is the necessary bijection between the root subspace with eigenvalue lambda and the root subspace with eigenvalue lambda bar. And because such a bijection exists, that implies these have the same dimension. So by the theorem from last time, we get the other stuff. So to establish this, I'll just explicitly write down the definition of this root subspace. Okay. Or in set theoretic notation, this is the set of psi and v such that minus a to the power of n, let's see, psi 0. And by definition of the image, this is the set theta psi in v such that theta minus a to the n psi equals 0. Okay, now because theta is injective, this set is actually just equal to what happens if I slap a theta onto this operator. Because in order for theta to map this to 0, because it's injective, that means that this is in the kernel of theta, which is 0. So I get back to that guy. Okay, now you can easily show, you can formalize this using induction if you want, that so theta commutes with the identity operator, and theta commutes with, I guess somehow I changed letters again, so maybe this A should be an H. Okay, sorry about that. Okay, so we know that theta commutes with identity and theta commutes with H. So if I want to commute theta through here, it mostly carries through, but the thing I have to be careful with is that by commuting theta from the left-hand side of these parentheses to the right-hand side of these parentheses, it converts lambda into lambda conjugate. Okay, now lastly, what we can do is, because theta is invertible, that means it's surjective, and that means that every vector in your vector space can be written as theta psi. So I can just give this vector a name, we'll call it phi. And voila, we've reached the root subspace corresponding to eigenvalue lambda conjugate. Okay, so this proves the lemma, and the lemma immediately establishes the upwards arrow in the theorem. Okay, so now let me see what the path of least resistance I found to the other direction was. So for the other direction, the way I found is to use the Jordan decomposition of the matrix A. So because I assume this thing is finite dimensional and has a Jordan decomposition. Now, we've mostly been talking about things in terms of root subspaces. Instead of talking about things in terms of root subspaces, we can also talk about them in terms of Jordan blocks, and you get something that's kind of equivalent. So to be more precise, you can relate the size of the Jordan blocks in the Jordan decomposition to the dimensions of the root subspaces. So, as a reminder, so given some matrix, there exists another matrix which is invertible. So this J is called Jordan normal form. And it can be expressed as such. So you can write it as a direct sum over blocks. Let's say it's an index set. So here, this lambda lives in the spectrum of H. This n indicates the size of the block, and this j indicates the number in enumeration of the block. So you can have many blocks of the same size and same eigenvalue if you want. To be more explicit, this as a matrix has the form of an n by n matrix whose diagonal entries are lambda. And then there's also a super diagonal like such, and the remaining entries I didn't write are all 0. So this is kind of a classical theorem from linear algebra. And then what you could do is you could try to characterize the number of blocks of size n, and according to the eigenvalue lambda. So I guess in this notation, that would be maybe the cardinality of this index set. Okay. Now, what I can do is, it turns out that this thing is equal to twice the dimension. Okay, wait, so I'm calling this size n. So this needs to be n. And lastly, I'm going to assume that n has to be at least 1. This is another kind of funny thing you can do when we start writing, start considering numbers as sets. Like I think before we had talked about how you could use just a single number to represent this set. Sometimes you don't want your set to start at 0. Sometimes you want it to start somewhere else. So the way you do that is you get rid of all the numbers that go before wherever you want to start. So just say this. This set n minus 1 is just the set of numbers starting from 1. And so this would be twice this dimension, and then subtract 2 things. And I can prove this for you if you'd like. Basically, the trick is to say that you first figure out the number of blocks of size greater than or equal to n. And so to figure out the number of blocks of size greater than n, you would say that you need something that lives at the end of a really big Jordan chain. And so that would have to live in some root subspace with dimension or with superscript greater than n. And so to make sure that, because this root subspace is a union of everything, of all of the eigenvalues, generalized eigenvalues of rank less than n, to make sure that you didn't accidentally get one of those, you have to subtract those out. So basically the first step to proving this would be to establish that the number of blocks of size greater than n would be equal to the dimension of the n+1 root subspace minus the dimension of the n subspace. So then to get the number of blocks of exactly size n, you would make it greater than or equal to n. So I guess turning to n-1, turning to n. You take this number of blocks and then you subtract the number of blocks that have size greater than or equal to n+1. So that's why you have this term subtracted, and you get another one of these. That's why there's a 2 there. Okay. But so the point is that so we gave one theorem characterizing the existence of these given dimensions of root subspaces. Because the number of Jordan blocks of a certain size corresponding to a certain eigenvalue can be given as this particular linear combination, you could equivalently give the theorem by saying that something is pseudo-Hermitian. There exists this non-degenerate inner product making your thing symmetric if and only if the number of Jordan blocks corresponding to a certain eigenvalue is the same as the number of Jordan blocks with the eigenvalue lambda bar. So sometimes this particular representation of that theorem is more useful to work with. Maybe to give a quick example. You can immediately tell that this matrix is pseudo-Hermitian. This one is symmetric with respect to something because it has two Jordan blocks. The one corresponding to lambda is the same as the one corresponding to lambda bar. However, this one is not pseudo-Hermitian. Because this one has two separate one-dimensional Jordan blocks corresponding to lambda. Okay. Right, so then the whole point is we've proven this direction of this theorem, and to prove this other direction, I want to use this result that so what we would do is say there exists a similarity transformation that takes H into its Jordan form. And in this Jordan form, we have, I guess, a direct sum. And we can write this further as a direct sum of two pieces. So here I can take the lambda such that the imaginary part is greater than 0. And by writing it as a direct sum of two of these pieces, we would see that the Jordan blocks are kind of in direct correspondence. So for every Jordan block in here, there is a Jordan block in here. And then the idea is to construct an antilinear symmetry from this decomposition. And the way to do that is you would just take some basis of this guy, let's say EJ mu. Mu with an n, and to define a map to be antilinear such that this guy equals so I can define an antilinear map that goes from a Jordan block in here to another Jordan block in there. And because the dimensions are the same, that gives us this thing being invertible. And then furthermore, you can show that this thing would commute with the Hamiltonian. Okay, so this is kind of the strategy to prove the equivalence of the existence of an antilinear symmetry and the existence of a non-degenerate inner product making the operator symmetric. Is this clear? So we talked about two natural classes of operators last time. We talked about these guys, and then we talked about a subcase as well, where not only does there exist a non-degenerate inner product, this non-degenerate inner product is actually makes your vector space a Hilbert space. And so this one, there was an equivalence theorem that said that the Jordan blocks, or no, that the root subspaces for lambda are in correspondence with the root subspaces for lambda bar. In the other case, we had an equivalence that said that was the necessary and sufficient criteria for a matrix to have real eigenvalues. Okay, so in this case, I found some equivalent criteria regarding the existence of a symmetry, and then I'll show you how it works in the other case as well. You need something a little bit stronger. You need something called an unbroken symmetry. Yeah. So this was the stronger criteria that we post on the second class of operators from last time. So if I have the existence of this thing, I get the necessary and sufficient criteria for a matrix to have a real spectrum. So there exists this, such that so what we can show is that, so we already know that this implies the existence of an antilinear invertible symmetry that commutes with the Hamiltonian. However, we need something stronger to get an equivalence, which is this unbroken thing. So what do I mean by an unbroken symmetry? I mean a symmetry that not only respects this property of the Hamiltonian, but it also it preserves the eigenspaces. So that'll be my definition of this term. So in general, this is not true because we've established that a symmetry will map a root subspace for eigenvalue lambda into a root subspace with eigenvalue lambda conjugate. So you can kind of see why imposing that this maps lambda just back into itself would be an equivalent criteria for the spectrum of an operator to be real. So already immediately you can kind of see from this that this would imply that lambda is equal to lambda conjugate. Yeah, so I guess actually so the proof of this statement basically just follows by combining the proof of this statement and this lemma. Is that clear? I can go into detail if requested. Oh, okay. So we have two equivalence theorems. Yeah, this one. Yeah, this one. And the idea is that this equivalence theorem follows from the combination of the perhaps weaker equivalence theorem and this lemma. And I mean, I can elaborate on details of that if you'd like. Oh, and I think one last thing I have to assume is that, so in this case, we know this implies that the matrix is diagonalizable. The way I've defined unbroken antilinear symmetry does not immediately imply that the matrix is diagonalizable because this root subspace might not be the entire root subspace. Some authors define unbroken antilinear symmetries such that it means that your matrix is also diagonalizable. I don't really like that as much because then you kind of lose this extra adjective that you can use to describe something. So I should also perhaps add up here in the terms and conditions that H is diagonalized. And then perhaps another reason why it's kind of nice is that you can make this kind of power of operator classes. So you can have things that are Hermitian with respect to a fixed inner product. So this is a strict subset of the things that are quasi-Hermitian. Did I use the word quasi-Hermitian before? I don't think so. Okay, sorry. So these things are the quasi-Hermitian guys. They're the things that become Hermitian when you choose a different inner product. So quasi-Hermitian things are not necessarily Hermitian because they're not Hermitian with respect to a defining inner product, but you could choose a new inner product that make them Hermitian. And then you have the pseudo-Hermitian. I think I used that word before. I could be wrong. So the pseudo-Hermitian guys are the guys that are symmetric in a general inner product space, which might not be positive definite. Okay, and so somewhere in between these two guys are the things with unbroken antilinear symmetry. And if you were to only define unbroken antilinear symmetry to imply that your thing is diagonalizable, then suddenly this tower wouldn't be as nice because these things would be equal. So I kind of prefer this. So yeah, just to clarify, the way that you get this equivalence for the up arrow, we already know that if you get rid of the word unbroken, that you get the existence of a non-degenerate inner product. If you add the word unbroken, it implies that the spectrum is real. So we have real spectrum and an inner product And then we suppose diagonalizability, and those three things puts us in this quasi-Hermitian case. So that's sort of the up arrow. And then the down arrow also kind of works exactly the same way. That if I give you something non-degenerate, such as this, then I get an antilinear symmetry, and the antilinear symmetry must be unbroken because the spectrum here is real, and for the spectrum to be real, that would mean that theta must map this root subspace into itself. If it mapped it into some other space, it would mean that the eigenvalue is not a real number. Okay. So we have these two equivalences. So I mean, I've been, I think for the last 4 sessions, I've mostly just been giving theorems, lemmas, definitions, such on. I haven't given a ton of examples. So the next thing I wanted to do was sort of summarize how everything we've been talking about works in the context of the simplest non-trivial example, which is for 2x2 matrices. And so I guess if you want, we can stop for a few minutes, just because this is kind of a complete story and I'm about to transition topics. So we can take a brief respite. To be a pattern of mind.
Lo que sí hay que está muy guapo es como las órdenes que quedaron
I know you just got here. Is this like, did I go too far? Is this clear? I can back up.
Yes, I guess it got clear. Yes, now it's quite clear.
Okay. So maybe one of the things that I didn't have at the time is like, so I define this antilinear symmetry, but I think to Nathan I have given a physical motivation for why you would care about an antilinear symmetry. So I did this. So this is a dynamical system. You do that, or you do that, right? And so if you take this process and you run it backwards in time, it looks like this one. But this one's also physically possible. So what you say is that this system exhibits time reversal symmetry, and the way that you mathematically impose time reversal symmetry is that. And so I explained why this thing needs to be antilinear. So in this dynamical system, because it's a real vector space, it doesn't make any difference. Antilinear and linear are the same thing. But yeah, if you go to quantum physics and you try to do it with a linear map, you run into problems. Which basically, so I have this constraint. So I wanted to be precise and try to derive this constraint from first principles. This constraint comes with a minus sign. Actually, maybe whoops. So I'll try to do it with I'm just summarizing the argument I gave you earlier to Kawe because he wasn't here. Okay, so if you try to have some linear map that imposes time reversal symmetry, so for this to reverse the direction of time, because there's this time derivative here, you need a minus sign. And so then you end up with some equation. I guess you would So if theta is reversing time, I also need a theta there. And then you end up with, anyway, I'm giving maybe too brief of a summary, but you get this expression. Okay, and this is a problem because it would imply that for every lambda in the spectrum of H, that minus lambda is also in the spectrum of H, which we know it just doesn't happen. That a lot of H has bounded below spectrum, but not bounded above. So if you try to do it with a linear map, it doesn't work. But if you do it with an anti-linear map, you'll notice that in order for me to insert this identity here, I had to split apart the I, and so that changes this minus sign to a plus sign. And then this thing commutes. So you get something that's okay. And then this still imposes restrictions on the spectrum. In the normal case, it doesn't. But in the anti-linear case, it does because it turns out that so this anti-linear symmetry maps the root subspace for lambda into the root subspace with lambda bar. So rather than mapping lambda to minus lambda, it maps lambda to lambda bar, which is okay. Yeah. Hopefully that gives a little more physical justification for. Okay, so our new goal is to find every 2x2 pseudo-Hermitian matrix. So to do that, the way I've been doing everything is first I prove a lemma that makes everything easy. So I'm going to start by proving a lemma that might not immediately seem related, but is powerful enough to sort of give us a boost towards figuring out what all of the 2x2 pseudo-Hermitian matrices are. So here's a lemma. So one way we like to characterize matrices is with characteristic polynomials. Okay, the characteristic polynomial, you'll remember, is this thing. I mean, maybe depending on your sign convention, you might define the characteristic polynomial with this one being negative and this one being positive, but modulo that. So let's define this as C for characteristic. This is a polynomial in one variable, which I guess we'll take over C, and A is some matrix. So if A is pseudo-Hermitian, then this polynomial has real coefficients. And so the way this is going to help us later is that we'll write down an arbitrary characteristic polynomial for 2x2 matrices. And by looking at the imaginary part of those coefficients, we can immediately roll out a bunch of matrices that have no chance of being pseudo-Hermitian. Okay. So the way you prove this lemma just follows from elementary algebra on sort of the determinant rules. So pseudo-Hermitian, we'll remember, means symmetric in a G space with G invertible. So that means is, so this is the supposition on the operator A. So then what we can do is write determinant lambda minus A. This is the same as the determinant of G inverse B. I just inserted a multiple of identity into here. Then I can expand this thing. So because the determinant is an algebra automorphism, I can multiply out these terms, and then they also multiply to 1, and so I'm left with this. Now, another rule of determinants is that the determinant of the adjoint is the complex conjugate of the determinant of whatever you're taking the adjoint of. So this would be determinant lambda conjugate. And now, what we started with was the characteristic polynomial like this. So this thing is equivalent to if you define the polynomial whose coefficients are all complex conjugates of whatever you started with. And so these are both functions of the same variable, therefore the coefficients have to be the same. So therefore the coefficients of this CA must be real. That proves the lemma. So now for 2x2 matrices, you can explicitly write the characteristic polynomial. Now, to make the problem sort of simpler or make the geometry more elegant, it turns out to be more natural to work in a basis for 2x2 matrices where the basis is self-adjoint. Because, I mean, we're trying to prove something about self-adjointness. So rather than working in, say, the canonical basis for 2x2 matrices, we're going to work in the poly basis. Okay, so what is the poly basis? The poly basis is given by this map, where I define probably time for a new chalk. Yeah, so these matrices satisfy many extremely nice properties. So one is that they're self-adjoint, which sort of is the relevant thing here. The products of these guys are also extremely elegant. So if I take any two of these three, they anti-commute, and moreover, there's a natural expression for the products of these things. So just to get to that, I'm also going to define some more notation. So I will say that, let's see. Given some function whose input is 4 and whose output is a vector space, I'm going to define a truncated function x vector whose input is 4 minus 1. The output is a vector. So this thing, I just throw away the 0th index. And then the other bit of notation I'll define is this dot product notation. So if I give you some x and some y, then I will define this to be this sum. And then I guess you have to assume that these functions are sufficiently nicely defined so that I can define this product. And so, for example, if these were both elements of an algebra, you could do that. Another way you could do it is if this x, instead of mapping into a vector space, it was mapped into just a field of scalars that are over a vector space. And then this vector space was over those scalars, then this would just be, yep. Xi, I'm sorry, thank you. Okay. So, and also this should go to 3, not 4. So the reason why I bring this up is that there's some compact notation for multiplication of 2 by 2 matrices in the Pauli basis. And that's as follows. Okay, so you get one term, which is the dot product. And then you get one term, which is the cross product. And I'm just going to check my notes real quick to make sure I didn't mess up this minus sign. But while I'm doing that, I can remark on sort of the beauty of this expression that we have three-dimensional Euclidean geometry encoded in this four-dimensional structure. So, I mean, nowadays, when we teach university students in such three-dimensional Euclidean geometry, we teach them it using this dot product and this cross product operation. This is sort of, I would say, I think, heaviside, if I'm not mistaken, was the proponent of doing it this way. This other way, you can show is mathematically equivalent to the algebra of quaternions. So if instead of inventing dot products and cross products, let's imagine some universe where you were taught about quaternions first, and you were taught about the quaternion product first, that somehow using that, you'd be able to get the dot product and cross product of three-dimensional vectors. This thing is in some sense, this is isomorphic to the quaternion product. Where this A dot sigma you should interpret as the imaginary part of a quaternion. So these are the three imaginary vectors. And rather than labeling the basis of the quaternions as ijk, this is I, this is j, and this is k. So this is just the quaternion product rule written in some fancy notation. So this matrix product rule is going to prove to be extremely useful for our subsequent purposes of characterizing 2 by 2 pseudo-Hermitian matrices. Okay, so now that I have that lemma, sorry. All right, I got confused. Okay, now that we have the lemma, we know that in order to have a chance at getting a pseudo-Hermitian matrix, what I need is something with a real characteristic polynomial. So let's say I take an arbitrary matrix, call it H, and I'll write it as follows. So yeah, and so I guess if I want to be really precise, because these scalars are complex numbers rather than real numbers, this thing you should understand is a biquaternion rather than just a quaternion. So the quaternions are a four-dimensional real algebra. The biquaternions are the four-dimensional complex algebra. Okay, so let's calculate the characteristic polynomial of this guy. To do that, at least for me, it's kind of simpler to do these linear algebra things the way I was taught, which is to write down a rectangle of numbers. So I'll just do that here. In the canonical basis, this would look something like this. So here I just used the canonical basis representation of the Pauli vector. So then the determinant of lambda minus h, you can readily verify comes out to this thing. Yeah. So in order for this to have real coefficients, because the A0 is going to end up being half the coefficient of the linear term in this characteristic polynomial, and I changed letters again. These A's should all be alphas. Okay, so we immediately know that alpha 0 must be real. And kind of a generalization of this statement. So alpha 0 is half the trace of this guy. a corollary of that lemma is that every pseudo-Hermitian matrix has a real trace. And that's because the coefficient of the highest power term in the characteristic polynomial that's not the monic term, that's not the highest degree term, is negative the trace. So from that lemma, you can immediately conclude that the trace of any pseudo-Hermitian matrix is real. And in this particular case, the way that I see that is with alpha 0 as a real number. So alpha 0 is the thing that's representative of the trace here. But then the next thing is that I need this square to be a real number as well. And then there's kind of a natural representation of what triples of complex numbers end up summing and squaring to a real number. And to do that, the best thing to do is to break these three complex numbers up into real and imaginary parts. And so for reasons that have absolutely nothing to do with electromagnetism, I have no idea what you're talking about. I'm going to define this this vector B to be the real part of the vector alpha, and then this electric field, E to be the imaginary part of alpha. And if you want to be really precise with the correspondence, you should probably put a minus sign in here. But I'm going to simplify my life a little bit and not introduce extra minus signs for the sake of physical elegance. So we're going to ignore that minus sign. So then what you can do is show that this sum of I of alpha I squared, if you split things up into real and imaginary parts, breaks up into two pieces. Oh, wait, no, I got it like this. So one is this Lorentz invariant scalar, and then the other, you get 2i e dot b. And then just another random fact is that for freely traveling electromagnetic radiation, one of the facts that you'll remember is that the electric and magnetic fields are orthogonal. So this thing should be 0, which kind of works out because we know that the coefficients of we want this characteristic polynomial to have a real coefficient here for the constant term. And so if this imaginary term is there, you'd run into a problem. So the way that you can impose that this quantity is a real number is to have orthogonal electric and magnetic fields. So this constraint gives us a real characteristic polynomial. Okay. So then my next claim is that, so I guess I can repackage all of this. So if I rewrite this, the Riemann vector as where this is the Zeeman Hamiltonian, like this, and alpha 0 B BI EI. You assume these things are real. The claim is that this actually is pseudo-Hermitian. So we know that in order for it to be pseudo-Hermitian in the first place, this determinant argument gives us this arrow. So this is kind of already proven. So I proved it this way. Now I'll prove this way. And to prove this way, I'll construct a gram operator that makes it pseudo-Hermitian. Now, I did give you a sort of tactic for generating gram operators last time, which is to start with this thing, and then look at the kernel of this guy. So I'm not gonna do that here, because I'm, just to sort of go with this purely coincidental, story of electric and magnetic fields, you end up running into the, electromagnetic stress tensor at some point if you do the calculation a little differently. So, so what I'll do is, okay, so the gram operator needs to be some operator satisfying this equality. Now I can just multiply the on the left by G everywhere to get an expression that looks like this. Okay, now I'll write G in the Pauli basis. So then we get some expression like this. And in order for this gram operator to be self-adjoint, we require that these coefficients must be real numbers rather than complex numbers. And in order to take an adjoint here, I think I have to have a minus sign here. So I need this to equal this. I'll just substitute in the Hamiltonian over here. Okay, so I mean, I can expand those things out right now, but I did it before and I found that by doing it before, I could organize the terms in a way that makes the resulting calculations obvious. So I'm just gonna copy from here, just for the sake of making it more readable. Okay. Let's see, so H adjoint G. So you get one term from multiplying this alpha 0 term into G, so you get alpha 0 G. You get one term from looking at the identity piece on this side. Okay, and then you're going to get a piece from multiplying out the respective Pauli vectors, and I have two different Pauli vectors on the left-hand side, so I'll multiply the magnetic one first. Let's see. So then I think what do we have? Remember the rule for multiplying two Pauli vectors is there's one term from the dot product of the two vectors, and then there's one term from the cross product of the two vectors. Here you have the cross product, and here you have the dot product. And then doing the same thing for the electric vector. This. And then we have one more term. So you have a minus I and an I, so that should turn plus E cross G. So assuming I haven't made any mistakes here, yeah, this looks fine. And already, okay, I think I wanted to organize it so that all of these parts are the imaginary parts. So I'll just move this over. This is what happens if you expand this out. And if you expand this out, you get, so you still get alpha 0 G. And then from the G0 terms, you get this. Now you get plus I G0 dot sigma. So you can see two of these terms are the same, but I picked up a minus sign on the imaginary term. Let's see, now we can multiply out the magnetic ones. Plus, let's see, so this should be the same. Yeah, now I have two more terms that show up. Yeah, this is a plus sign now. This has a plus sign. And let's see, so I get okay, so if I'm not mistaken, there's a bunch of stuff that cancels out. Basically, all of the real parts should be the same. And then if we look at the imaginary parts, so let's see, I think we need two separate things to hold. So first is that the coefficient of this guy must match the coefficient of this guy. And the only way that's going to happen is if we get this constraint. And then there's another constraint that comes from matching the Pauli vectors of both of these sides with each other. So that should look like, so this thing needs to equal that thing, but that thing ends up just being the negative of this thing. So the sum of these two things must equal 0. And then you can rearrange it so you get this. Okay, so you get two equations, and if you can find a real vector in these equations, then you found a gram operator. Okay, so then there's a question of how do you solve these equations? And that should be relatively straightforward because these are linear equations in the variable g. So you can end up repackaging these things as one 4x4 matrix acting on this vector. And then this matrix turns out to be the stress tensor I was talking about. Let's see, so these are all 0. I think this is negative. Oh yeah, so you need to find the kernel of this matrix. Okay, now one immediate thing that you can see is that assuming that the magnetic field vector is non-zero, that the kernel has dimension at most 2, because the rank of this thing will have dimension at least 2, because you have at least 2 linearly independent columns if you have a non-zero magnetic vector. Now, if you have a non-zero electric vector, but a 0 magnetic vector, then it's the same story. This and this give you rank 2. So immediately what you can see is that the rank of F is greater than or equal to 2 if one of these is non-zero. Okay. So that means the kernel has dimension at most 2 because of the Reg nullity theorem. So then what I can do is I can explicitly generate solutions to this. And kind of the way to do that is as follows. So now I'll just tell you what the 2 elements of the kernel are. Basically, what you need is that the G vector is orthogonal to E. So you work in some basis, which is the magnetic vector, and E cross B. That forms the basis of everything that's orthogonal to E. And then if you plug this in here, then you end up finding that this must be, if I'm not mistaken, this. Yeah, okay, I got all the minus signs right, that's great. So you can prove that that is in the kernel of F. So you can show that this clearly satisfies these. This one, you have to use a triple product identity of 3-dimensional vectors in order to get, because you have to take a cross product of this with this guy, but it's not horrible. But this cross product automatically vanishes. Okay, so now what I've done is I've explicitly shown that every 2x2 pseudo-Hermitian matrix takes the form of this Riemann vector. Now, as for understanding of why this is rhyming with the math of electromagnetism, I'll remind you that so kind of there's a couple things that we're after. This whole thing is talking about conserved quantities, and in the theory of electromagnetism, there's a natural conserved quantity, which is the speed of light. And in order to describe that thing, you need an indefinite inner product. You use this norm for space-time where you say that time-like vectors have negative length and space-like vectors have positive length. So you have a conserved quantity, and in order to describe it, you have to use an indefinite inner product space. So kind of that's maybe a deeper reason for why this math rhymes. And I'm sure that if you thought about it for longer than I did, you can make the correspondences much more precise. Okay, so then the next thing is, this is how the story works with regards to pseudo-hermiticity. And then I taught you all this stuff earlier today about antilinear symmetries. So you can ask, well, what kind of antilinear symmetry does this thing exhibit? So to describe that, I'm not going to directly talk about this guy. I'm going to simplify it a little bit. And then in the simplified version, the antilinear symmetry story will become more clear. The way to simplify this, it turns out that you can use similarity transformations to rotate these vectors. And that shouldn't really come as too much of a surprise, because you could imagine that this thing is like a Lie algebra element of SU2 cross SU2. And SU2 we know is, SO3 is the double cover of SU2. So we should be able to implement SO3 Lie group operations on this SU2 Lie algebra element. So if you want to be more explicit, so it turns out that in the theory of 3-dimensional rotations, every 3-dimensional rotation leaves at least one vector invariant. This is the so-called Euler theorem. And that actually generalizes to an odd number of dimensions, that if you're in an odd number of dimensions, a rotation will always leave one vector invariant. Let's give that vector a name. So I'm going to talk about a rotation about this vector is invariant. And then the other thing is there's an angle that you can rotate around this vector by. So maybe this is some vector that exists in 3-dimensional space, and then you rotate by an angle. So there's something that says that every rotation can be expressed in this form somehow. And in this representation, turns out this rotation can be implemented as this. And then I'm assuming that this vector n hat is a unit length, but if you don't want to do that for some reason, you can just divide by the length of that vector. So the idea is that this is a unitary. So that means that it's invertible. And furthermore, what it means is that you can do this operation. So you can construct this similarity transformation of your matrix, and this ends up having the effect of performing rotations on E and B. This is something that you can verify at some point if you'd like. The way that you would prove this is using the infinitesimal Baker-Campbell-Hausdorff formula. Okay. So using rotations, I can find a similar Hamiltonian. But so using rotations, these vectors still need to be orthogonal to each other. If I rotate, it doesn't change the dot product of these two guys. So it gives me some freedom to choose E to be along a certain axis and choose B to be along a certain axis. But I still have to preserve the angle between them. So what I'm going to do is I'm going to choose theta in n hat such that, so B, I'll just choose it in the x direction, which I guess in this language, this would be E1. And I'll choose E be in the z direction, which in our language would be E3. So these things are still orthogonal, and I can always choose them in this way by doing a suitable rotation. Now I have this matrix. Okay. So it turns out that the antilinear symmetry of this guy can now be constructed. It would be this. So this K is sort of the canonical anti-unitary involution, and what that means is it does this to the basis vectors. Let's see. So this acts as complex conjugation in the canonical basis. And so this means you have theta H is, so you have alpha 0 theta. Alpha 0 is real, so I don't have to worry about this complex conjugation doing anything on it. Plus, so this is real. And sigma x as a matrix has real coefficients, so I can commute this canonical conjugation with it, and I get sigma x squared a bx. And another nice property of the poly basis is not only are these guys Hermitian, but they're also involutions. So this is just identity. So again. And then here I'll get plus. So I'll just leave the k over here for now. I have plus k I e v sigma x sigma z. And the other way, these are the same. The next one is the same. And then the next one I have I e z sigma z sigma x. Okay. So then there's some care that has to be taken. So you have to compute this product I sigma x sigma z, and Up to a minus sign, it should be this matrix. It should just end up being I times poly y. And this is a real matrix that commutes with A. And then this one should be backwards because the poly matrices anti-commute. So you would pick up a minus sign, but the minus sign is dealt with because this K is in front of this I. Anyway, these are equal. So I've constructed the anti-linear symmetry corresponding to this matrix. One way of perhaps physically interpreting what this does is, so this matrix, they've physically realized it as modeling, okay, so here's a physical system that's modeled by that Hamiltonian. You could have these two optical fibers. And so in the optical fiber, it's just like a channel that you could send some radiation down. And you can put them very close to each other so that there's some chance that the radiation can quantum tunnel from one to the other. And you could put some slab in here. So the material, this slab that you put in the middle, would dictate the rate at which the radiation could hop from one channel to the other channel. And then, so if you just want to model the radiation hopping from one side to the other, that would be given by, I guess, the tunneling piece. You can just represent it by sigma x. You could say that like a state that's in E0 is representative of some radiation that exists in channel 0, and a state E1 is representative of some radiation that exists in channel 1. So choosing a Hamiltonian that has a sigma x term has hopping between these two. Now you could also you could have something shooting radiation in here. So you could have like some laser that shoots radiation into this left channel. And so what that would sort of amount to is you have some gain of information, and you would represent that using this kind of Hamiltonian. So so to have gain in the left channel, you can have say an entry of 1 here. And so if I just do this, then this won't have an anti-linear symmetry because the spectrum of this thing is not symmetric. So then what they do is they make this channel lossy. So they have some attenuation over here, and physically that would be modeled with a Hamiltonian like this. So we have some gain in the left channel, loss in the right channel. And the Hamiltonian looks like this. So this Hamiltonian looks exactly like that. And then maybe pictorially, what you could do is instead of drawing these complicated squiggles, you could just say, okay, well, here's channel 0, here's channel 1. They're coupled like this. This one is a gain, and this one has a loss. So what the effect of theta does is, so K will change the sign of this imaginary unit, which changes this plus sign to a minus sign, and this minus sign to a plus sign. No, I don't need to change the labels. And then if I hit it with this sigma x changes the roles of 0 and 1. And I think I changed these again. I don't know why I did that. You'll notice that this schematically is the same as this. So maybe physically, in this particular physical setup, what this anti-linear operation is, it's a combination of a time reversal symmetry and a spatial reflection symmetry. So this composition this decomposition of the time reversal operator. In this system, they would give it a name PT. So they would call this KT, and this sigma X is P. So if you hear people talking about PT symmetric systems, they just mean something that commutes with an antilinear operator that has this form. So then I guess there's some non-trivial thing, at least to me, which is, so people will call this time reversal, but maybe from a mathematically purist point of view, this thing is the thing that actually does time reversal. There's kind of a nuanced point there that depending on, like in this physical system, if you have some understanding of how time actually works, maybe you want to call this thing time reversal instead. Okay, so then I talked a little bit about how this thing has this antilinear symmetry, which we call PT. And then there's this last thing that we talked about, which is a difference between an unbroken and a broken PT symmetry. So then you can ask me, okay, well, how do we see that in the context of this 2x2 Hamiltonian? So broken and unbroken antilinear symmetry, you see that from the eigenspaces. And so I could go through and explicitly calculate eigenspaces and show you that they're invariant under this guy, but I think there's something that's maybe geometrically a little prettier that will display the point even better. So in the 2x2 case, there's a very natural geometry for what eigenspaces look like, which is given by something that you either hear it called the block sphere or the Riemann sphere. So mathematicians call this thing the Riemann sphere. The Riemann sphere is a homeomorphism between two very simple topological spaces. So one is the complex projective line, and one is the sphere. So the sphere is why it's called the Riemann sphere. The complex projective line, what is that? That is, in some sense, you can imagine it as a set of all one-dimensional spaces that exist inside of a two-dimensional complex space. So this is a natural, like, if you want to talk about like a one-dimensional eigenspace of this guy, it's natural to represent it as an element of CP1. To be more explicit, I could define this set as follows. So it's the set of bands of vectors in C2 where V is a two-dimensional non-zero vector. So this is the complex projective line, and the Riemann sphere is a way of mapping this into the sphere in a homeomorphic way. Sorry?
Union with one point is the infinity point. I've seen it like that, but I don't know if it is the same thing.
Yeah, I do see what you're saying. Okay. So if you look at these guys, so these you can represent as psi0, psi1, or I don't know why I switch letters so let's say V0 and V1. And so because the only thing we care about is the linear span, we can say that this is equivalent to this. I can just divide by V1. So this is where the C comes in. However, this division only works if V1 is non-zero. So then there's some extra point in here, which I guess you called infinity, which in this notation would be this. Yeah, and so this is also a homeomorphism as well. You could define the complex projective line like this, and everything is homeomorphic. I guess the advantage of this is that it's clear how to define the complex projective line CPN rather than CP1. Whereas here it's kind of unclear,
Yeah.
like what CPN would look like. Do you just attach a single point to CN minus 1? So I can elaborate on, I can give you an explicit formula for this homeomorphism. This homeomorphism is given as follows. I can define the orthogonal projection onto span V. And then I can take the Hilbert-Schmidt inner product of this with the Pauli vector. So this is a map that takes something that's in CP. And the output is going to be a collection of 3 numbers. And I'm only going to look at these 3 because if you look at the trace with respect to Pauli 0, you don't get anything interesting. You just get the trace of an orthogonal projector, which is going to be a half. If I'm not, it's going to equal 1, right? So you can kind of just ignore that. So then this defines a tuple of 3 real numbers. These numbers are real because this is Hermitian and this is Hermitian. So you have the trace of a product of 2 Hermitian guys, which is real. And then using the properties of the Pauli vector and the properties of orthogonal projections, you can show that these 3 numbers, when you add their squares, you get identity. So this is the homeomorphism that takes you from CP1 to S2. And to show that it's, I guess, an isomorphism that you can go backwards, what you can do is, starting from this point Si, you can construct a projector, which is this sum. So this is sort of the inverse of the homeomorphism, that I start with a point on the sphere and I end up with a projector. And then from the projector, I can take its image, which is the point in CP1. So anyway, the point of all of this is that, so I could just tell you what the eigenspaces are, but by using this homeomorphism, I can instead draw the eigenspaces of that guy as points on a sphere. And they look kind of like this. So what I can do is I can consider the ratio, or I can consider this Hamiltonian as dependent on Bx and Ez. I'll choose Bx to be, okay. I'll choose units so that this thing is equal to 1. So for Ez equals 0, so the sphere, there's, I guess, you have these 6 sort of cardinal directions, and I don't know. The way the picture looks the prettiest is if you choose this one to be the x-axis. So if we start at Ez equals 0, the eigenstates of sigma x are going to be these 2 points on the Riemann sphere, the plus x and minus x spots, which hopefully isn't too much of a stretch to imagine. You could work through the math and prove it. But similarly, the eigenstates of sigma z will correspond to these 2 points on the sphere, this plus z and minus z. So as you increase this variable Ez, it turns out what happens is the eigenstates move along the equator of the sphere. They merge here, and then they will approach these two poles. Okay, so you see a qualitative behavior change at this merging point, which is called an exceptional point. We'll talk more about exceptional points next time. So this is maybe a hint of what's to come, that you start with two eigenvectors. They eventually coalesce at a single point, which you call an exceptional point. And then afterwards, they branch off in a different direction. Now, the next thing that you can show is that the PT operation that we have here, its effect on the Riemann sphere is to take some point, let's say up here, and to reflect it about the equator. So the way that you can geometrically understand PT symmetry breaking is that PT is unbroken on this equator. That if you apply the PT operation to an eigenstate that's on the equator, you get back to yourself. But after you leave the equator, this eigenstate will get mapped into this eigenstate. So the eigenstates are no longer invariant under PT after they leave the equator and cross through this exceptional point. So maybe this is kind of a nice geometric visualization that you can have a model that's a function of some parameter, which in this case would be the ratio of these two guys. As you tune that parameter, you can pass this point, which is a so-called exceptional point. And as you pass it, PT symmetry goes from being unbroken, where the eigenstates are invariant, to being broken, where the eigenstates are no longer invariant under the PT operation. Another signature is, so this is what happens if you look at the eigenvectors. If you look at the eigenvalues, they look kind of like this. So I chose Bx to be 1, so I can plot lambda in the spectrum of H as a function of Ez. And this 0 will just be alpha 0. That's well defined to be the 0 of this Cartesian plot. So these things are real up until this so-called exceptional point, which is the same merging point up there. This is that Ez equals 1. And then after this point, the spectrum branches out into the complex plane. So this is a graph. This graph is relatively easy to prove. We in fact already have the characteristic polynomial of this guy. I might have erased it, but the characteristic polynomial, remember, this is going to be you can verify this is the characteristic polynomial. This is something we did earlier. And so the roots of this occur at these points. And so I have this kind of square root behavior. So I start from plus or minus 1 in the units that I chose on that graph down there. Once the exceptional point is here, Bx is Ez, where instead of having two distinct eigenvalues, you have one eigenvalue. If you tune Ez to be past Bx, this thing becomes imaginary and the spectrum branches off into the complex plane. So there's this kind of very unique spectral property that PT symmetric pseudo-Hermitian operators can have that normal Hermitian operators cannot have. You can have these exceptional points where the spectrum, you have this breaking of symmetry, where you have like a real spectrum on one side and a complex spectrum on the other side. Yes? Okay. Do we have any questions on this? Okay, so anyway, I hope that this 2x2 example sort of helps illustrate the concepts that we've been talking about last time in some way that makes things a bit easier to visualize. We have a little bit of time left. I have some extra maybe fun facts that I've prepared in case I had a little bit of extra time, but they're not directly related to this. So I can show you the fun facts if you want, or if you have any questions about this, this would be a good time. Okay, so I guess fun fact number one is we've been talking about symmetric and isometric operators for the most part. So there's other operators that mathematicians are interested in. For example, there's positive operators. So one question you could have is, how do you characterize the spectrum of a positive operator on an indefinite space? And what is the definition of a positive operator? So positive operator is defined in a way that's probably familiar. That this thing is greater than 0 for all x. And then it turns out you can show that theorem in the G space with G invertible, you can show that the spectrum of P is real. And so symmetric operators in indefinite space can have a potentially complex spectrum, but positive operators have a real spectrum. However, you can't have positive operators with negative spectra. The proof of this theorem is pretty straightforward. You have this. This is just the symmetric property. You can multiply G in here and consider this operator. So this product operator is a symmetric, and if you plug this into the defining relation for a positive operator, it turns out that this is also positive. This thing is positive operator. So then what we know is that the spectrum of GP, this thing is positive. And then kind of the trick is to go backwards, to go from GP to P. So I give this thing a name. In the book I was reading, it was called D. And then there's some relation which is like G inverse D equals D. So therefore the spectrum of P is the spectrum of G inverse D. And because D is positive, it has a positive square root. And then another property of spectra is that so the spectrum of AB and the spectrum of BA are equivalent everywhere except for 0. So this is one nice fact about the spectrum of operators that we've already established that, so G is self-adjoint, so the symmetric is real. And then I conjugate it by some positive operator, and conjugation will not change the reality of the spectrum. And in fact, what you could do to make that precise, you could write this as a difference of two positive operators. Something you can always do for self-adjoint, guys. And then conjugating this positive operator by d1/2 will just give you a different positive operator with positive spectrum. Conjugating the other one gives you a positive operator. But if I take a difference of two positive things, I might get a real number instead of a positive number. So therefore, this is real. So the spectrum of positive guys is real in G-spaces. Okay, so that's kind of the fun fact to finish on for today. Now we're getting pretty close to 4:30, so I think we can stop. Okay, Edgar, I can send you the bibliography for the course I think I sent an email with like maybe 10 books or something in there. But I've also been making off the cuff remarks about random papers. And so one thing I can do is I can go through the notes that I use to prepare for these sessions. I can look for places where like, oh, well, here's a paper that summarizes this theorem, or here's where this place was first proven. And I can attach those papers to the email thread that has the books. So that's probably what I can do for you. Okay. If nothing else, I'll stop the recording.